Hello, today I'll be talking about the work of myself and my advisor James Kloss on the problem of finding missing tests. Test suites are valuable artifacts for developers since they give confidence that the implementation is correct, allow for changes to be safely made, and can be used to augment documentation. However, writing test suites is difficult and error-prone, leading to missing tests, which are tests that should be there but are not. Missing tests ultimately result in a less effective test suite that does not test important use cases and could fail to reveal faults. The typical way of finding missing tests is to use coverage tools, which are able to indicate a subset of the places that require more tests. However, covered code could still be missing tests, and further, coverage tools fail to give developers an indication of how these places should be further tested. Knowing how to test something is just as important as knowing that it should be tested in the first place. To improve on this situation, we propose a static analysis-based approach that takes the application and test suite and produces missing test reports in 4 steps. The first step is to identify siblings within the application. Siblings are code entities that should be tested the same. The next step is to find the relevant tests for those siblings in the test suite. The third step takes those tests and produces summaries so that they can be compared. This is necessary so that we can tell which siblings have been tested in the same way. The final step identifies which siblings have missing tests and produces missing test reports. The main benefits of our approach are that we provide example tests as a starting point to address missing tests. Each report is justified with some level of support, and we are able to find missing tests for code that is already covered. Automatically identifying siblings and not relying on coverage are major improvements over prior work. The following slides will explain each step of the approach in greater detail. The first step of the approach is sibling identification. Siblings are code entities that are accomplishing the same goal within the application and therefore should be tested the same. For our approach, we define a sibling group as a method and all of its overriders. Although inheritance is a convenient way of establishing a sibling relationship, it is not the only method that can be used to form sibling groups. In this example, the method remove and its overriders become a sibling group. Next, we find the relevant tests for those siblings. We use a coarse-grained heuristic for this, which is that any test that calls a method gets associated with it. While there are other methods that trace tests to code, this method has the advantage of simplicity and a low false negative rate. In the example, the tests in the pink boxes are associated with the method that they call. Next, we summarize the tests. The purpose of this step is to allow us to be able to compare tests. More specifically, we want to know when tests have the same purpose. In this example, the 2 tests have the same purpose, which is to test the behavior of trying to remove an item from an empty collection. However, they have different names and bodies, making it necessary to have a way to compare them. To compare them, we summarize both the test name and body. To summarize the name, we divide the words of the name into 3 categories: subject, response, and modifiers. We use a keyword-based approach to decide which category a word is in. For example, words following should are generally the test response, and words following when are generally scenario modifiers. To summarize a test body, it is transformed into a set of method calls, which allows for variability to exist between 2 similar tests. Additionally, we inline any setup code or helper methods into the test body. After lifting the tests into these comparable representations, we use a simple majority to vote to establish which siblings are missing tests. In this example, one sibling is missing a test represented by the given body summary with the support of 2 out of 3 siblings. Similarly, using the name summary, we find that a sibling is missing a test represented by the given summaries, again with the support of 2 out of 3 siblings. Let's say some irrelevant text calls one of the siblings. Due to the fact that it will not gain enough support, it will not be reported missing. This helps to filter out noise introduced from our coarse-grained test-to-code heuristic. We evaluated our approach using 10 open-source Java projects. This table shows the 10 subjects used in our evaluation. The classes and methods columns give an idea of the size of the application, and the groups and siblings columns show the number of sibling groups and siblings found within each application. To generate the missing test reports from the subjects, we implemented it as a IntelliJ plugin. We then manually classified each report as a missing test, candidate for refactoring, or erroneous report. A missing test report indicates that the sibling can have this test. A report is a candidate for refactoring when the sibling already has a similar test, but this test deviates from the rest of the group. For example, if the majority of siblings have test A, but one sibling has test AB, it may be advisable to refactor that test name. An erroneous report occurs when a sibling does not need or cannot have this test. For example, some siblings may exist in a class with extended functionality that another sibling does not have. In this case, it cannot have a test for that functionality. Of the approximately 2,100 siblings found, approximately 1,000 had at least one report. The average number of reports for these siblings was around 2. This figure shows the distribution of reports by category for each subject separated by the support level of the report. For example, TableSaw has approximately 150 missing test reports at the 0.66 support level. The main takeaway is that the vast majority of reports are useful, and most erroneous reports come from 2 projects. This indicates that there are project-specific factors that can influence the effectiveness of the approach, but these factors do not have a major negative impact overall. Next, we want to compare to the most commonly used method for finding missing tests, which is coverage. This figure shows the number of reports whose corresponding siblings have the indicated level of coverage. We can see from the bar on the right that most siblings with reports were fully covered, meaning that coverage would have been of no help in finding these missing tests. This figure shows the number of methods in each project that are uncovered, partially covered, or fully covered. The highlighted columns show the number of coverage reports a developer would receive in the form of uncovered or partially covered methods. Depending on deciding which of these to focus testing effort on and how to test them is a daunting task. Our approach can be thought of as providing developers with a quick way of adding useful tests to the suite without having to sift through potentially thousands of reports. So in summary, this work contributes a novel approach to the problem of missing tests that addresses not just what is missing a test, but how it can be tested. Our evaluation shows the effectiveness of this approach by examining the reports of 10 Java projects and comparing them to coverage. Thank you.